You remember when we were talking about limits, and when you had to find a limit algebraically, often we got, 0 over 0, right? So for example, limit of like x squared minus 4 over x minus 2, something like this, right? This was a problem from way back when, like limit as x approaches 2 of x squared minus 4 over x minus 2, right? When you put 2 in there, what do you get? 0 over 0. Well, it's not undefined, it's indeterminate, right? And remember we said when you get 0 over 0, we call it indeterminate form, which means it could be undefined, it could be DNE, or it could be defined and you get an actual value. So what we had to do in that case is we had to use algebra, and we either factored, or if it was a square root, we rationalized, remember? So in this case, I could factor this and I get x minus 2, x plus 2 over x minus 2. That goes away, and then when you put 2 in there, you get 4. Remember, that's how we did it way back when. Okay? So now, we're gonna talk about a brand. Oh, I canceled the wrong one. So we're gonna talk about a brand new way to do it right here. So when you put 2 in there, you get 4. Okay? Now, what L'Hopital's rule does is it uses derivatives to evaluate the same thing. Okay? We're not going to go through like the proof and how you do it, but we're just going to do it. So look, using L'Hopital's rule, okay? So I have the limit as x approaches 2 of x squared minus 4 over x minus 2, right? What you do is you just take a derivative of that numerator. And when you take a derivative of the numerator, what do you get? 2x, right? And when you take a derivative of the denominator, what do you get? 1. Now, what was x supposed to be? 2. So when you do 2 times 2 over 1, what do you get? 4. So you see that? It's much cleaner, and you can get that answer.
It's always been like that?
So that's L'Hopital's rule. It's always been like that. We just never taught it to you. Okay? And you never do. In no course is it taught in the beginning. That's why this is in chapter 8. It's after you've taken a whole course of calculus. Right? So with chapter 7, technically Calc 1 finishes. Calc AB, Calc 1, whatever. And then, right, this is taught afterwards. Okay? I know. And there's a reason why we don't teach you the rules of those power rules before the definition of the derivative. Remember way back then, how did we do derivative? It was limit as h approaches 0 of f of x plus h minus f of x over blah, blah, blah. And then we said, oh, x squared is just 2x, right? Because if you want to learn calculus, you have to know calculus. You have to know the definitions of these things. It's not just about shortcuts. Okay? All right. So let's find. Okay. So this first problem, right? Limit as x approaches 0, sine of x over x. So if you put in 0, here, then I have sine of 0, which is 0 over 0, which doesn't work. So what we do then is we're going to take a derivative, and the limit symbol will stay. Limit as x approaches 0. Take a derivative, take a derivative. So cosine x over 1. And now when I plug in the 0, cosine of 0 is 1. So cosine of 0 over 1, that's 1 over 1, it equals 1. All right?
When do we take Oh, we take out the limit once we put in the
Right. That's the same as before.
Right, okay.
Okay. All right. So this one, it's the reciprocal of what we were doing up there. So when you put 2 in there, you get 0 over 0. But this is going to be the limit as x approaches 2 of 1 over 2x, 1 over 2 times 2, 1 over 4. Okay, question. How do you know when to use it? When you get 0 over 0. No, wait. So here, again, tangent of 0 is 0, sine of 0 is 0. So we're going to take the derivatives of top and bottom. And the derivative of tangent was what? Good. Secant squared x. And sine of x is cosine x. So cosine is the easier one, I guess. Cosine of 0 we know is 1. Secant is 1 over the cosine, so it's 1 again. So that's just 1. Okay? All right. Here, when I put 1 in here, I get 1 minus 1, 0, over 1 minus 1, 0. 0 over 0, indeterminate form, we have to do this. So, this one here, okay, so the numerator is just 1. The denominator, this is x to the 1/2, remember? So when I take the derivative, it's 1/2 x to the negative 1/2. Okay, so let's just see what that looks like really. That looks like 1 over 1/2, what does that mean?
2.
It's really 2. X to the negative 1/2 is x to the positive 1/2 on top, right? So that's just 2 root x. Oh, what have I forgotten? Limit. Yes. So here, when you put 1 in there, you just have 2 times 1, 2. Okay? Much cleaner than before. What would we have done before with L'Hopital's rule? What would you have done before L'Hopital's rule? For this particular one. Right, but no, there was a way to solve it. What was, you had to rationalize. So, okay, so listen. You might be asked this problem, and you might be asked, solve it using L'Hopital's rule, solve it with that L'Hopital's rule, right? So how would you do it that way? We multiplied both root x plus 1, root x plus 1, remember? And then that was the limit as x approaches 1, x minus 1, root x plus 1 over what do you get on the bottom? X minus 1, those go away. You put 1 in there, you get 2, right? So you see the benefit. Okay. So sometimes you take a derivative, all right? And then you're like, oh my God, I got it, L'Hopital's rule. You take a derivative, you plug in the value, you get 0 on top, 0 on the bottom, again. So what do you do then? Repeat, okay? So we call this, it's called the stronger form of L'Hopital's rule. So basically, repeat if you get 0 over 0 a second time. Or a third time, or a fourth time, or a fifth time. So a friend of mine who, let me stop. Okay, so apply the stronger form of L'Hopital's rule to find the limit here. Okay, so let me teach you a little bit of notation here. Often, so here you put in 0, you get 1 minus 1, and that's 0 over 0, right? So often, people do one of two things. You either write here that it's 0 over 0, meaning it's indeterminate form, and it's sort of understood that you're going to do L'Hopital's rule, or people will just write, LH for L'Hopital's rule, okay? So here it's the limit as x approaches 0. And when I take a derivative of the top, what do I get? Sine x over 2x. So now I put in my 0 and I get 0 over 0. Oh my goodness. Well, even better. I actually prefer it that way because I get to do L'Hopital's rule one more time. So L'Hopital's rule again. Limit x approaches 0. Cosine x over 2. Finally, that x went away. Now, when I put in the 0, you get 1/2. Cool, right?
Yeah.
It is pretty cool. Yeah. All right. So this one, always check if you are going to get a 2, because don't assume that just because it's under the L'Hopital's rule section that it's going to be a 0 over 0. Sometimes you could just plug it in the first time and you just get the number, right? So here it's 4 minus 8 plus 4. Oh, look, it's 0.
What happens if you use
8
L'Hopital's rule?
minus 24 plus 16. Oh my God, it's 0 over 0. I know what you're going to ask. Let me answer that later. So what now? L'Hopital's rule. This is the limit as x approaches 2. So the reason why I have this one in there is, don't think it's only for like those rational ones, or you know, the square root ones, or the sine or cosine ones. 2x minus 4, 3x squared minus 12. You got to do it again. Now when you plug in the 2, you get 4 minus 4. Can't do that. 12 minus 12. 0 over 0. So you got to do it again. 2 over 6x. Usually when one of the, yeah. So it's 2 over 12. 1 6. Do you have to simplify though?
Yeah.
Yes, you do. What happens if you don't? There you go. You know me. Well, 1 if it's a test, because there's more points to lose. But no more quizzes, so that's a moot point. Okay.
Wait, we only have 2 more tests. One more test.
One more test and a final. That's it. So here, 0 over. Wait, you don't get 0 here, do you? On the bottom? Yep. E to the 0 is 1 minus 1 minus 0. Okay. So we're going to apply L'Hopital's rule, and we're going to get 2x over e to the x minus 1. But that's still 0 over 0. So now it's limit x approaches 0, 2 over e to the x. So see, like if these had higher exponents, we could have like just kept on doing this forever and ever and ever. So it's 2 over e to the 0, 2. Okay, so 0 over 0 gives us, okay, so this is a subtlety that most students and lots of adults, who are we kidding, most adults don't get, because if you didn't get it as a student, you're not going to get it later as an adult. A number over 0 is undefined. That's for sure. 0 over 0 is not 1, and it's also not undefined. So 0 over 0 and 3 over 0 are not the same. Okay? 0 over 0 is one type of indeterminate form. Another type of indeterminate form is infinity over infinity. Because you can't say that's 1, can you? Like you can say 50,000 over 50,000 is 1, because you know exactly how much 50,000 is. But do you know how long infinity is? How about like if you think you're at infinity, but then your friend is one step ahead of you. They're also at infinity. How could you cancel both of those out? You can't, right? Yeah.
Is this put in the same category as like imaginary numbers?
No. Imaginary numbers are strictly the square root of -1. That's it. Yeah. Okay, so another type of indeterminate form is infinity over infinity, right? Again, this is not equal to 1, all right? Not equal to 1. But you could also use L'Hopital's rule for that. Okay, so look at this one. ln of x as x approaches infinity. So, ln, what's ln of x look like? Ln of x looks like this. It goes up slowly, but surely it goes up. And if you're at infinity, it's infinite. And then x squared at infinity is also infinity. So this is infinity over infinity. But we can't have that. So we're going to use good old L'Hopital. So limit x approaches infinity. And somebody told me the derivative over there. 1 over x. That's the derivative of ln of x over 2x. And here the math sort of turns into algebra, not much calculus at this point. Right. So 1 over x over 2x is 1 over x 2x. All right? You do combine it. So that'll be the limit. Is it 1 over 3x?
No,
1 over 2x squared. And then as x in the denominator gets infinitely large, the entire fraction gets infinitely small, right? Imagine if you had one pizza and you're dividing it among infinite people. How much is each going to get? 0. Okay?
Well, let's keep on.
So 0. Okay?
Oh, so if it's 1 over
Well, remember, this is a limit, so it's the understanding of approaching
It'll
that
never
value.
touch 0.
Right. But again, that's the understanding of a limit.
Right.
Just do it once and then.
For this case, yeah, we were saved. We only had to do it once. If you have to do it again, you do it again.
How do you do that?
Well, because when I plugged in this number, when I plugged in infinity here, I didn't get 0 over 0. I didn't get 1 over infinity over infinity. I got a value. 0 is a good value to get. All right? It's just as good as any other number. Aaron and then Eli.
For example, for the next one, we don't know how to graph this.
So you don't really have to graph any of these, but if you do remember, so tangent has those leaves, right? So like it goes up to infinities, and then secant, remember it was like those U shapes and it goes up. So this is going to be infinity over infinity. So we're going to use L'Hopital's rule. And this is going to be the limit as x approaches pi over 2 of 1 is going to be 0, but what's the derivative of secant x? Look at you guys. You remember. I'm so proud of you. Jason. We're not talking about that because you need this for this test, right? Okay, so tangent of x, secant squared x. All right? So now, what happens now?
Now we plug in pi over 2.
Tell me. You can cancel one secant from here, one secant from there. So this is the limit. X approaches pi over 2, tangent x, secant x. I always love it when students remember things they learned a year ago. So now, tangent of, okay,
Pi over 2.
what's going to happen here? This is a little bit of trig now. What's tangent of pi over 2? It's still infinity. Secant is still infinity. But you know what? Like tangent and secant, they're made of other functions, aren't they?
Yeah.
What are tangent and secant made of?
Sine over cosine.
Yes. Sine over cosine. And 1 over cosine x. And the golden rule in math is if you have a complex fraction, if you have identical denominators or identical numerators, you can cancel them. So this is just the limit as x approaches pi over 2 of sine of x.
Wow.
And now we put in the pi over 2. And what is sine of pi over 2 these days?
These days?
How much?
1.
1.
Just 1 of these.
So that's just 1.
Sine is y, cosine is x.
Yes.
Yeah, because C comes first in the
Oh.
alphabet. That's where people do
Oh. Okay. I hate that stuff. Okay. Okay, so is this infinity? It doesn't look like infinity over infinity. What's e to the infinity? Infinity. But this one, it looks like it's getting smaller because you take a square root of infinity, but what is that? It's still infinity, right? Okay. So this is infinity over infinity. So another way, is you can write that. And now we're going to do L'Hopital's rule. So this is going to be the limit as x approaches infinity, e to the x over, we're going to do the same thing here. Remember, this was x to the 1/2. So it's going to be 1/2 x to the negative 1/2. So this is the limit as x approaches infinity. Where is the 1/2 going to go? It's going to be a what?
2.
A 2.
It's going to be 2 root x.
2 e to the x times root x. What now? E to the x is how much? Infinity. Root x is infinity, so this is just a very large infinity. So we say it's infinity dne, right? Remember, infinity is also like dne infinity.
Do you have to put both of them or can you put both?
Okay, so again, the age-old question. I'm okay with this. I'm okay with this. Not okay with this, but okay with like this one as well, in parentheses, is how we did it before, okay?
Wait, when do we do the L'Hopital rule twice with infinities?
So
Yep.
it's infinity over infinity again. Shh. So here I get limit as x approaches infinity of 6 over, okay, 2 to the x. Listen. So 2 to the x, what's the derivative of e to the x? E to the x. So the derivative of 2 to the x is 2 to the x times ln of 2. Don't ask. Don't ask. This is new. I didn't cover it. I think next year I will cover this as well. Huh?
No, she said she.
Are you sure it's not 2 to the
I am sure, yes.
1?
I'm positive. I'm positive. I'm as sure as I am of
You
my
still
name.
solve this on our own in the first one.
What is that? Is that times?
Yeah,
Okay,
times
so
L.
now, yeah, so the derivative of a number to the x is a number to the x times ln of that number. So a to the x, the derivative is a to the x ln of a. And that in itself is just a beautiful thing, but we'll leave that alone. So now, as x approaches infinity, this is another one of those things. You have 6 on top, a constant old 6. Here you have 2 to the infinity, which is infinity, times, ln of 2, that's still infinity. So you have 6 over an infinitely large denominator, and that'll be how much for the whole fraction? 0. Now, a few things. I know I've said this before, but suppose you get to a point where you have, limit as x approaches infinity, I don't know, 1 over e to the x. Okay? How much is this? 0. Now, I know I've talked about this, and I hope I don't have to repeat it again, but I never, ever, ever, ever want to see anybody doing something like this where like you plug in the infinity. It is never, there is not any situation where that's allowed. Okay? So please, 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 we never do this. We never do, infinity, no. All right? Only if you get it as an answer, but never as part of like an operation. Never. Okay? So please don't plug it in mentally. All right, so this is where I'll stop.